Thank you very much. Good morning, everybody. My name is Ankit Tyagi, and I work at Eriez Manufacturing. And today I will be talking about my topic, which is towards developing frequency robustness via domain-enriched AI for industrial metal detection applications. So again, this was a collaborative effort between Eriez Manufacturing. The first author here, Suhrid, could not make it to the conference, so I'm presenting here on his behalf. He did a lot of the work, and we collaborated with Dr. Vishal Monga, who's a professor at Penn State University in the United States and a professor in electrical engineering. So I would like to first set up the stage for the problem statement. I want to talk about Eriez Manufacturing and how metal detection kind of plays into that role of the portfolio that we have put together. So Eriez Manufacturing is a global leader in separation technologies. They've been around since 1942, which is a long time ago. We have a lot of presence around the world, so located in United States, but have a global presence in a lot of different other countries. We have about 1,000 employees globally and about 400 employees located in the United States. And then, since the inception of the company, we've been providing technical solutions to our customers, catering towards industries that are in food manufacturing, mineral processing, aggregates, recycling, pharmaceuticals, and things of that nature. So as I mentioned, we have global presence around the world. We do have a subsidiary location located in Vancouver, which is very exciting. So I'm going to be after the conference, I'm going to go pay a visit to them. But in terms of what we do, we provide all these technical solutions that are ranging from permanent magnets potentially utilized in food industries, but all the way to large suspended electromagnets that are utilized in aggregates industry, and also very large equipment for mineral processing. And within that really broad product portfolio, we do something small, which is called metal detection, and that's one portion of our product portfolio. And I'll be talking about that today more specifically. So balanced coil metal detection is a critical control point in a lot of manufacturing processes, ranging from food industries to plastics to pharmaceuticals. And essentially, at the heart of it, it is a balanced electromagnetic field that is being created by this device via the use of a transmit coil and two receive coils. And you can see that the signals that are generated on this device are sort of complex in nature. They're time series signals. You can represent them in two different formats. So you can have a polar representation, where the circles represent the magnitudes, and then the counterclockwise direction represents the phase. So in this example here, you can see that the overall phase of this is kind of oriented just greater than 90 degrees with an amplitude of about 1200 or so. And you can kind of break this down into time series signals as well. So essentially, it's made up of two physical parameters that we're tracking all the time. One is the permittivity of the material that is passing through the detector, and one is the conductivity of that product passing through the detector. And you can kind of see the time series representation of these signals with the figure on the right. So the state of the art for a lot of these equipment is still threshold-based detection schemes. So a lot of the equipment that is out in the market is getting installed in these industries still rely on threshold-based methods. And really at the heart of it, what you're looking at is some sort of detection scheme that looks at if a magnitude change. So if you have an amplitude detection, you might be drawing up two control points, and then you're looking at whether the amplitude crossed that line, or you're looking at a phase change that happens along the process. So you expect a typical phase pattern to occur and when a product passes through. And if there's any deviation from that and it gets outside the threshold, you're basically counting that as a metallic contaminant that's being inspected. But the problem with this methodology is that since these measurements are highly sensitive to, say, size, shape, type of metal that is being passed through, they are really, really sensitive and could lead to a lot of false negatives or false positives all the time. So it's really a big deal in the industry to make sure that we are, in fact, detecting pure contaminants and not having a lot of false positives or false negatives in the process line. So that's one aspect, but signal processing in these pieces of machinery is also affected by several key parameters. And these are some of the really heavy hitters that affect the ability to intelligently describe what is happening at the equipment. So one thing is called product effect. So think of food industries. There's cheeses and meats that are present, and when you're packaging them and you're processing them, they typically have a very conductive behavior to them and in response to the electromagnetic field. So they have their own signal that gets created. It's so much so that it's larger than any small contaminant that might be able to be detected on these machines. So in other words, the product effect is overshadowing the type of signal that we're interested in, which is a small, tiny trace of metallic contaminant. So that product effect causes a lot of problems. It's overshadowing the small contaminant signals. And in the figure on the bottom right here, you can see that this is a typical clean conductive product. So think of it being like a meat product that's being inspected at the detector. In the middle, you have a very small, tiny stainless steel contaminant signal. And you can see that the phase is quite different. The amplitude is quite different between the two. But when you put the two together and you pass them through the detector, they actually produce a signal which is very, very similar to the signal of the clean. So there's really no way for the equipment or for even a human to distinguish what are the differences between figure 1 and figure 3 here. So it's very, very similar to one another. So that's one aspect, but there are several other aspects that affect the ability for the detector to intelligently describe what's happening and what is being passed through the aperture. So things that are ambient to the environment, so temperature and humidity can really have an impact on signal processing. There are physical product variations that could actually also attribute to that change. So things like product size, product orientation, type of product, how conductive it is, these all factors affect the ability for the detector to do a good job at detecting whether there's a contaminant or a clean product. And then finally, we have systemic parameters, such as detector parameters. So things like the electromagnetic operation frequency of the balanced-coil detector, the belt speed, the aperture opening, all of these things are internal to the system itself that affect signal processing from a standpoint of detecting contaminants versus clean products. Today, I will be focusing on the detector frequency as the main talking point. And as I mentioned before, it is a key part of the detection algorithm. So in this figure on the right, you can see that for a clean product, which is conductive in nature, at one particular frequency, you're getting an amplitude and a phase that's represented by this figure. But as you change the operation frequency, you're getting a very different signature. So it's actually higher in magnitude. The phase is slightly changed. And that same behavior sort of happens with the contaminated product. So this is a clean product with a bit of a metallic contaminant present in there. You see kind of like I would body shame the signal, but it's a fat signal. But then as you go to another frequency, it actually stretches out. It becomes really thin and has a large amplitude to it. So it is not really a bad thing for us to have multiple frequency perspectives, because at the end of the day, we want to be able to distinguish between what is a clean and what is a contaminated product. And the multiple frequencies actually allow us to have a much better perspective on finding characteristics that help us decide between a clean versus contaminated product. So because the threshold methods sort of failed to generalize and understand this concept, we turned towards deep learning. And deep learning is important here because we have better chances of doing pattern recognition, superior feature extraction. Now, when you add a little bit of domain enrichment to it, a bit of domain knowledge to it, you actually are allowing for low training requirements for these models or these algorithms to do better, to have better accuracy. And then overall, this helps us do improved metal detection with fewer false positives or fewer false negatives at the end of the day. So before I jump into that aspect of frequency robustness, I do want to talk about, we did have a paper out in IEEE Sensor Journal earlier this year, which specifically looked at the product adaptive models. And in this case, we devised some very clever product adaptive models to essentially negate the effect of products that are having on the signal processing side of things. So we devised this method that enabled us to look at subtle contaminant signals and improve the metal detection accuracy without having any significant impact on the overall accuracy in terms of false positives or false negatives. And essentially, with this work, we were able to not only detect between clean and contaminated, but we were also able to detect and go beyond what type of contaminant we can detect, whether it's coming from ferrous, non-ferrous, or stainless steel. This was great, but it kind of fell apart when we actually looked at frequency of the operation of the detector. And by the detector frequency change, you're actually inducing some sort of data drift that happens in our signals. So essentially, you can see in this figure that the phase plots of these of the same product at two different frequencies, there's a bit of a difference in behavior of these signal trends. Same thing happens on the magnitude side, where you can see that the peaks are quite different from one another. And again, threshold methods will very much so fail at this effort, but also our prior product adaptation model was not able to generalize over this process. So how do we fix this problem? This is something that we really need to address to make sure that we can scale up across different types of machines and equipment and at different operating frequencies. So we have a need for a frequency robustness in these types of models. And again, the goal is to scale up, but also to leverage the complementary information that is present between two frequencies of electromagnetic spectrum. And at the end of the day, we want these models to be lightweight and efficient and to be able to have real-time deployment on the edge devices. So we do this by implementing something called a 2D convolutional squeeze excite time network. It's a mouthful, but essentially at the heart of it, I want you to have three takeaways from this framework. So we actually have a 2D convolutional neural network block, which has shared weights. And essentially what it's doing is it's looking at the magnitude and phases and kind of coming up with a spatio-temporal structure to preserve what mutual information is present between different features as well as different time series steps. Again, we are implementing shared weights here, so that allows us to have essentially a way to minimize the number of parameters that we need to store. Then we pass on that information to an SE block, or the squeeze excite time block, where we're coming up with better feature maps to kind of look at very reduced features. And then the excite part here is essentially exciting or enabling looking at the only features that really matter for us to do a better job at detection. So by doing so, we're kind of looking at the really important features that are required. And then at the end of it, we pass it through a bi-LSTM block, which is essentially looking at the observations bidirectionally in terms of temporal sequences and what features really make a difference in terms of doing a better job at classification. So this is sort of like the pipeline for data collection. We pass products through a metal detector, much like in this picture here. We collected that data on a computer, and then we essentially utilized that to do annotation and pre-processing. We utilized two distinct frequency combinations and had a really good distribution between clean and contaminated products. We looked at ferrous, non-ferrous, stainless steel, but even with those three types of contaminants, we looked at three different sizes to really mimic real-world scenarios and what we could typically expect in a production line. And here's my slide on the experimental results. So you can see that we compared and benchmarked against a black box deep neural network. We compared also against our product adaptation model, which is the ECF, and compared that against to our 2D CSET model. And you can see that the mean performance metrics averaged over multiple experimental runs shows that our current methodology does really well. Now, you'll be surprised that it's 100%. It's not really realistic, but there's a reason behind that. It's because we are using a much smaller data set. If we scale across different products and different machines, then we will probably see some different numbers here.
2 minutes.
So essentially, thank you very much. So essentially, what you can see is that the black box method here has a higher bias towards classifying products as clean, and they lead to higher false negatives. So we're actually countering that by implementing some sort of domain knowledge here, and also making sure that we are leveraging across different detector frequencies that can be operational on the unit. So with that, the conclusions and feature work for this type of work. So as I said, we've implemented a spatio-temporal structure to preserve the two frequency signals for enhanced feature learning. We've implemented share weights to make sure that we're compacting our parameter set that is required for these models. And then overall, we're doing a much better job than we were, before in terms of being able to look at more challenging data sets, more real-world scenarios, and try to really scale up the algorithms that we're developing for our equipment. Some of the feature efforts here are directed towards self-supervised learning, which allows us to have a bit more of a robustness across varying frequency settings. And at the end of it, we're also looking at additional physical feature spaces that will allow us to kind of scale up across a whole bunch of other problems that we encounter in typical industrial applications. With that, I'd like to acknowledge my co-authors. Again, Suhrid Das, he did a lot of the work for this work effort, this paper, and we collaborated with Dr. Vishal Monga. He's a professor at Pennsylvania State University. And at this point in time, I'll be happy to open up it to the audience for questions.